today I'm going to talk about a theorem so crazy that if I told it to someone 300 years ago, about the time when the relationship between derivatives and integrals was discovered, they would think I'm absolutely insane. And of course, I'm talking about the fundamental theorem of calculus, more specifically the second fundamental theorem of calculus, and it is just a statement that the definite integral from a to b of f of x dx equals capital F of b minus f of a, where this capital F function is a primitive of a function f of x. And what does it mean? Any function that's a primitive of a function, if I have a function f of x, then a function that is its primitive, we can call it capital F of x. This is just such a function that if I take its derivative, I'll get back to the original function f of x. And of course, there's an infinite amount of primitives, because if I have the function, and I had a constant c, when I take the derivative, the constant disappears. So, I still get back even f of x plus 66 was still, if I take its derivative, I'll still get back to the function f of x. There's an infinite amount of primitives, but that is all that this, fundamental theorem of calculus is saying. And students think, it's kind of so normal, because usually, when we're learning calculus, we first learn, that we have a function f of x, then we can take its derivative. So we have x squared, we can take its derivative, and that will be 2x, or we can take its integral, and that is going to be x cubed over 3. And that is what we learn. And then we learn that, you can also take a definite integral, from bounds a to b. So that would just be your integral, what you found, if you evaluated at 5 and then evaluated at 4, this will give you the area between the function, from 5 to 4. But that is such a crazy statement. Think about what this theorem is saying for people, because people back in the day never knew the connection between integrals and derivatives. They just knew about derivatives. And then, the classic way to find area, under a function, if they wanted to, is they actually had to sum rectangles. They had to make, approximation rectangles and then sum them together. There was no, there are also other techniques to find area under a function, but they were also tedious, and they never gave you the correct. It was impossible to find the exact area under a function. If it was like, a special smooth function, if it was a square, of course you could find it. There was no way to do that. And then all of a sudden, the fundamental theorem of calculus comes around and says that the area, that this represents the area under a function. So, I have a function f of x, and I'm looking at it from intervals a to b. Well, the area under this function can be represented by just the difference of another function in its y-axis. So, I have another function, I can call this capital F of x, and again, I'm looking at the same interval a to b, and I'm saying that, this over here will be f of b, this over here will be f of a. I'm saying that the area under a function f of x can be represented as the y difference of another function. So just the difference in the y-axis of this other function, which is already crazy. How can 2D area be represented by, just a 1D difference of this function? And then an even crazier thing I'm saying is that this function is a primitive. This specific magical function is such that if I take its derivative, I'm going to get back to the original function which I'm trying to find the area under of. This is such a crazy statement. It makes no sense why, integrals, why area under a function, and why rates of change, why they should be connected at all. They're two completely different worlds, but yet, it works, which is so crazy. And I'm going to prove this theorem first, and I'm going to kind of be trying to prove it in a way that, like, how they did back in the day. They didn't exactly prove it like that, but it was a similar thought process. And then I'm also going to show another way on how to prove it, which was using, which is kind of not really prove it, but another way to think about the fundamental theorem of calculus, which kind of gives you a different perspective, because I just think it's so cool. But yeah, so first of all, let's go back in the past, and let's say all we know back in the past is we know that we have a function, and we know that we can take its derivative. Derivative of the function is just the limit as, I can say the limit as h goes to 0 of f of x plus h minus f of x over h. That is just, the instantaneous rate of change. People know that. And then, people, of course, they realized that, we can find functions, we can find other functions such that, when we're studying one function, we can find another function, special function, such that if we take its derivative, we get to this function again. That's what people are noticing. They're playing around with that, but they don't know at all how it's connected to area. And then, of course, there's a whole other part of math where just people try to approximate area under functions using, there's some circle methods, there's some rectangle methods, just people playing around with that. But these two worlds are completely unconnected. Well, one thing people do know, or, a similar thing, is Lagrange's mean value theorem. And that's what we're going to be using. And Lagrange's mean value theorem is just a very, very, very simple classic theorem. Let me just say Lagrange's mean value theorem. That is just a theorem saying that if we have any function, any function f of x, and let's say that this function is continuous on this interval, and we're looking at it from an interval a to b, then if I take the general slope of this function, so the average slope, so basically if I take this slope, which is just going to be f of b minus f of a over b minus a, or this is just y2 minus y1 over x2 minus x1. That is just this is the bottom, and then this y difference is the top, is the classic equation for the slope. Well, I'm saying that this general slope equals the actual slope of this function at a certain point. So we can see over here, if I shift this line downwards, at this point over here, this special point, I can call C. This point C is somewhere between our interval. Oh, I wrote the double thing. This point C is somewhere between our interval A and B, and it's such a point that our function, the derivative of our function f evaluated at this point C, will have the same slope as this general slope over here. So we'll have the same slope as the general slope of the function f of b minus f of a over b minus a. That is what Lagrange's mean value theorem is saying. So basically the instantaneous rate of change of the function will at one point equal its average rate of change on the interval. People knew that. That's a classic thing. And now let's say we're just playing. Let's say we're just saying we're trying to study this function f of x, and we found its primitive. So we found a special function capital F of x such that its derivative equals f of x, and then we're just playing around with it. So we're studying this function capital F of x. Let's say capital F of x looks like this, and we're looking at this function on the interval a to b. We're just kind of playing around with it, and let's say we make partitions of this interval. So we split this interval up into little partitions. And these partitions, this I can call A, I can call x0, this I can call x1, this I can call x2, this I can call x3, again, this I can call xn, let's say this continues, and this final B I can call xn. So I just split, we had this interval over here, and I just split this interval, so I just made a partition, and this partition will be x0, x1, up to x capital N, and this is a partition, I did n splits of the interval AB. And of course, I can make my partition bigger. If I make n equal to 1,000,000, then I can make 1,000,000 such lines in between A and B. So I have 1,000,000 of these x's, and I just make a different partition. Let's just say I do this, and then I can apply Lagrange's mean value theorem to each interval. But again, here we have the interval I1, here we have the interval I2, here the final one is the interval IN, and all these intervals are exactly the same big. And I can apply Lagrange's mean value theorem to each interval, which just means that I know that there exists a special point epsilon n, I'm gonna call it epsilon n, in an interval IN, such that this will be a point such that my function capital F, the derivative of it evaluated at this point epsilon n, will equal the actual slope of the function at this interval. So f of x n minus f of x n minus 1 over x n minus 1, xn minus xn minus 1, and that, xn minus xn minus 1, and that thing of course just equals delta x, and delta x will be constant. The delta x will be the same for each interval. So I'm just looking that I'm looking at a specific interval. So let's say I'm looking at this interval over here. I know that this interval, if I zoom in again, if I zoom into one interval, I'm gonna get something like this, let's say, and then I know that the average rate of change of the function, which will just be the function evaluated at the point xn, for example x3, minus xn minus 1, so x2, this will be the average rate of change, which can be this. I know that there exists a point in between this interval, x2 and x3. So there exists a point epsilon. Inside this interval in. So for example, this interval here, such that the derivative of my capital F function, this is my capital F function, at this point epsilon will just equal its average rate of change. I know that, and this over here, xn minus xn minus 1, that will just be delta x. We can apply Lagrange's mean value theorem to do this. We can do this for every interval, but let's just see what happens. Well, what is the derivative of our function? Well, we said that we found this special function such that its derivative actually equals the function f of x, which we're kind of studying. So we know that this is the same thing as just saying the derivative of f at the point epsilon n, and now this equals f of xn minus f of xn minus 1 over delta x, and now I can multiply delta x on the other side. So what I get is that the derivative of f at the point epsilon n times delta x equals our capital, our antiderivative function f of n minus f of x n minus 1. But now what is this? This over here looks kind of interesting. Well, this is a function capital F of x. Then I can, draw also our function, our function, let's say, looks like this. Our f of x function, again, I'm looking at it on the same interval a to b, so this is the same large interval, and exactly how we split this interval into partitions of our capital F of x function, of our primitive function, I can split this into the same size intervals. It will be the same size interval, it will have the same partitions x1, x2, x3, and so on. Well, this, let's say I'm looking, at this interval. Let's say, if n was 3, so xn minus 1 was 2. So I'm looking at this interval over here. Well, I know that this point epsilon is somewhere in between here. So f of x, the derivative of f at the point epsilon, this will have a value somewhere here. I can draw it with a different color. This, this will just be our function f evaluated somewhere here times delta x. Well, delta x is just the size of each interval. So that will literally give me this rectangle over here. This will give me the area of this rectangle. And I'm saying that the area of this rectangle, in our function, in a random interval, will equal our primitive function at the point evaluated at the point f of x, so x3 minus the primitive function evaluated at the point f of x minus 1, so x2. So I just found out that I can approximate this rectangle area using a primitive. So I can approximate the area of a rectangle of our function f of x using a primitive, just evaluated at each endpoint, which is kind of crazy. This gets me thinking, well, can I just do this for every interval now? Can I sum up all these intervals? Because of course I split our function capital F of x into n intervals, between a and b. So let's just say, well, now, oh my goodness, I just got an idea. I'm gonna try to sum up all these intervals together, and when I'm trying to sum them up, what do I get? I get the sum from n equals 1 to n of f of epsilon n times delta x, and delta x is obviously just a constant. It depends on your partition n, so I guess I can do capital N here. Delta x, just if I make a partition of 10 points, then the x will be, a certain size. If I make my partition bigger, x, the intervals will obviously be getting smaller because I need, more intervals in between a and b. But this thing is just a constant, and I can say that this equals the sum from n equals 1 to m of our, of our primitive function f of xn minus f of xn minus 1. This is kind of what I find out. So, the area of these rectangles of a function f of x, just a bunch of these rectangles, this area will equal to the sum of the difference of our primitive functions, at each point. But of course, this will be a big sum, it's going to be confusing. What is this sum exactly? Well, actually, no, it's not. This over here is the telescopic sum. Telescopic sum. And why is that crazy? What is a telescopic sum? Well, let's see what happens if I write these in these terms all together. F of xn from n equals 1 to n, well, that will be f of x1 plus f of x2 plus f of x3 all the way to plus f of xn. That is, if I apply the sum to this guy, and if I apply the sum to this guy, I will get, xn minus 1. So I'm going to get negative f of x0. When n equals 1, this will be 0, minus f of x1 minus f of x2 minus f of x3 minus all the way to minus f of xn minus 1. Because obviously when I get to n, x will be n minus 1. So I get this sum over here, and we can see x1 negative f of x1 plus f of x2 negative f of x2, x3 negative f of x3. All of these terms cancel. The xn minus 1 will also cancel with the term here. The only terms that remain are f of xn and f of x0, which are exactly the endpoints of my interval. This is b, and this over here is a. So what I'm left with this telescopic sum is just f of b minus f of a. And this is a remarkable result. This is so clean. I just found out that the area of my rectangles from n equals 1 to n of my partition of of a random point, so f evaluated at a random point epsilon times the size of the interval, this over here will be equal to just our primitive evaluated at b minus our primitive evaluated at a. So I can, if I have a partition, I can find the area of this function using these rectangles, which is pretty cool. But then the craziest thing is, there is no limit to how small this partition can get, because here we chose a pretty big partition, maybe the estimate isn't that good, but I can choose a partition n for n to be bigger and bigger and bigger. I can make smaller and smaller and smaller, splits of this function, so that the approximation of the area will be better and better, because we're going to be adding more and more precise rectangles, and the telescopic sum will always evaluate to f of b minus f of a. Because this telescopic sum, even if n is like 1,000,000, if we evaluate 1,000,000 small rectangles, what we're going to see that all the in-between things cancel each other. We will always just get that the first element survives and the last element survives. So no matter how small a partition gets, this telescopic sum will always equal to f of b minus f of a. So what we're saying is, if we take an infinite amount, if we make our partition delta x infinitely small, if we make our delta x very, very small, so we can make it equal to dx, infinitesimally small, this will give us the actual area under a function. It's really, no one has ever time to have a function and sum up a million small rectangles, because back in the day, if you wanted to get a good representation, you had to sum up, hundreds of thousands of small rectangles if you wanted to find the area. But here, I'm just saying that, I can make this partition really, really small, and this value is going to stay the same. So this value over here, what it actually gives me, it gives me the exact area under the function f of x. That is such a crazy result, because again, if delta x gets smaller and smaller, if we're talking about the Riemann definition of the integrals, if I choose a partition smaller and smaller and smaller, I can get, as the limit as capital N goes to infinity of these partitions, so I can just say of these sums with my partition and f, well, at the limit, this will just give me the integral from a to b of f of t dt, or f of x dx, whatever. This is how the Riemann sum is defined. This is literally just the Riemann sum, and at infinity, this gives us the exact integral. People didn't yet know what a Riemann sum is, what this notation of an integral is, but they realized that this thing will always be constant, so they can take more, smaller and smaller rectangles, more precise rectangles, and eventually they're going to get to this. So this literally gives you the area that, if you find the primitive of your function f of x and just evaluate it at your interval, that will literally give you the area of your function in between this interval. That is such a crazy result, and this completely changed the game. Every single other method that people had for finding area under functions were just completely thrown in the trash because they were useless now. This is the best possible area. If you can find, people knew what derivatives were, and they already had methods for finding primitives. People had methods of finding primitives of functions. They just didn't really know why it's useful. Well, now all these methods of finding primitives just became insanely useful because they help you find the area under a function. Now now the fundamental theorem of calculus is complete, and this is just notation. People didn't really have the integral notation anymore, but now we made this notation. So we have the integral of f of x dx, and this equals f of b minus f of a, and this over here gives us the area. So now this definite integral completely changed the game, and then that's why we also introduced then the indefinite integral. Then people started actually making this notation because it became really useful to find the primitive. This sign over here, this symbol just gives you this gives f of x plus c, and that means this notation over here just gives you the set of all primitives of f of x. So this special notation here that then we started using because we saw how useful primitives are, just gives us the set of all primitives of the functions. If you take the derivative of these functions, no matter the constant, you'll get back to your function f of x. But this area game, this fundamental theorem of calculus, part 2, it completely changed the game. This is the end of the proof, kind of. With Riemann sums, if you say that this integral goes to 0, you get exactly the integral. This is the proof finish, basically. But I still want to, you can stop watching the video now. But I still want to talk about it a bit more, just because of how crazy it is. Now I want to forget about this and I want to look at it in a different way. If anyone is still interested, I want to see. I guess I want to go back into the world where we had two different types of math. So one of the types of math was just finding the area under a function. So let's just say I have a function here, f of x, and I have a special function a of x, and this function I'll call the area function, and this function will just be such a function that it's gonna find the area of our function f of x from a point a. So I can say this is a point a up to point x, and this point a is constant, and this point x is just anywhere to the right of a, and this function a of x just finds the area under this function. And I want to just have a mental game, which I have a function like this. I don't know exactly how it has to look like, but I have a function like this, and I want to see why on earth the derivative of this function will have to be. Why would the derivative of this function have to be my function f of x? Why on earth would this area function have that just looks at the area from a point a to the point x? Why would this function have to have a derivative, which is this function itself? So if anyone's still interested, you can still listen. But basically, I can say that this function a of x equals just the integral from a to x of f of t dt. Again, the people in the past didn't have this notation of the integral sign yet, but I'm just using it now. It basically so it makes sense for us. This function is finding the area from the point a up to the point x, and the point a is fixed. And now I want to see how does a small change in this area function look like. So if I have this function, and then let's say if I want to find how the area changes when I don't look at the point x anymore, I'm going to put it a bit more to the left. I don't look at the point x anymore. Now I look at the point x plus h. We know how much does our area increase by? How much does our area function increase by? So I can look at our area function ax plus h. So So, this whole area minus a of x, which will be, this area over here, our OG area. And I can see what this change will equal. Well, kind of the special realization you can do, I mean, this will just be the integral from x to x plus h of f of t dt. But, kind of the realization, if your h is small enough, if you take the limit as h goes to 0, this will just approximately equal your function f of x times the value h. Because again, look, I can zoom into my function a bit more. So, I have a function here, and I'm looking at its area. This is the point x, then I'm looking at the point, x, like x plus h. Here I'm exaggerating how big h is, but h would just be the size of this interval here, and this change will just, if I put h close enough to my function, if h is very, very, very close, this function at this point is basically a straight line. No matter if the function is increasing or decreasing or about constant, if I zoom in close enough, for any function, the function will basically be a straight line, at that point. Which means that if I wanna, calculate the area of this rectangle, I just have to, calculate it by its, I have to, multiply it by its height, and its height will just be f of x. Its height will be f of x, because again, f of x and f of x plus h are so close to each other. Here I have f of x, here I have f of x, here I have f of x plus h. They will be so close to each other. They will basically have the same height. So the height of the rectangle will be f of x, and the base of the rectangle will just be h. It will be this over here. So the change in my area function will just approximately be f of x times h, if h is very small. And then if I take, if I divide h, so if I divide by h over here, I'm gonna get that a x plus h minus a of x over h. Well, that would just equal, that will approximately equal our function f of x. But now, what is this over here? That is just the definition of the derivative. If I take the limit as h goes to 0, that is exactly the definition of a derivative of any function. F of x plus h minus f of x over h. That is how we define the derivative of a function. So the limit as h goes to 0, this won't be an approximate sign anymore. That will be an equal sign. And now we can see that our area function, we just thought of an area function. Well, this area function has to have a derivative, and its derivative will exactly be a function f of x. Again, provided this function is continuous and integrable. But this area function has to have this derivative, which is absolutely crazy. It seems like these two constants shouldn't be connected, but they are connected. And now, how can we prove the second fundamental theorem of calculus with this? Well, a crazy thing is we know that our function a of x has a derivative f of x, and now we know that we can say that our function a of x equals another function f of x plus c. I can say that a of x equals this function over here. I can do that. And then f of x is just a slightly different function. And if I take the derivative of a of x, that will just equal the derivative of f of x plus the derivative of c. But c is a constant, so that will just go to 0. So the derivative of f of x equals the derivative of a of x. So these two functions have the same rate of change. They have the same property. They're just shifted. One is just shifted up and one is shifted down. They're just shifted from one another. But now, a crazy thing is I can now evaluate my function a at the point a, and that will just be again the integral from a to a of f of t dt. Because again, remember, our function a of x finds the area of this function from this point a onwards. So if I find the area at the point a, well, then the area will just be a straight line. It will be 0. So this will be equal to 0. But a of a, we said a of x can equal f of x plus c. So that equals f of a plus c, and that equals 0. So what does c equal? C has to equal negative f of a. I just put f of a on the other side. C equals negative f of a. So our area function a of x equals f of x minus f of a. If I choose a c such that they have the same derivative, and if I evaluate the function at the point a, I see that c has to equal this. And now, let's say I want to use my area function to find the area at a point b. So I'm looking at a point, let's say b over here. This is a point b. I want to find this area from a to b. Well, that will just equal to a of b will literally just equal to the integral again from a to b of f of t dt, and that will just equal to this over here. So f of x becomes b, f of b minus f of a. That is exactly the fundamental theorem of calculus. Now we can discard this function over here. We just started with an area function, from a to any point, and we just found that we just found the second fundamental theorem of calculus. The integral from a to b of a function f of t dt equals any function which is a primitive of our function f of x. This isn't our function a of x anymore. This isn't a special function which only finds the area from the point a to x. from a to x. This is now a function. F is just any primitive, so f is just any function such that its derivative will be our function f of x. And we just showed the fundamental theorem of calculus this way. It is, it is such an interesting theorem, and the connection seems so easy and so apparent. But it connects two worlds. This connects the world of finding finding area under f of x, and then a completely different world, which is finding the rate of change of f of x, the instantaneous rate of change. And these two, they seem like such completely two different tasks, but they're actually connected. That is why I think the fundamental theorem of calculus is really cool and really beautiful. I probably skipped over some historic facts and some things. And maybe you can prove this end thing a bit more rigorously if you wanted to, but that is the theorem in a nutshell. I just think it's really cool. I want to make this video a bit longer just to kind of talk about how crazy of a theorem this is, and how if you think about it in a perspective from the past, we think this is so normal, but it's not normal at all. This is such a crazy relation, and it completely builds up calculus, and then makes it into this big field, and it finds it just completely destroys every single other area under the graph method because of how powerful this one is. So this is really how, when calculus started. Well, actually, don't quote me on that, but I feel like this is when calculus really became a big thing, when people found this out. So yeah, that is it. Thank you for watching.